Okay, in this video we're going to look at magnetic fields, or the basics of magnetic fields, because you may or may not be aware of them, and we'll go through this nice and in as much information as needed at this level. So we'll start off with the basic bar magnet. So a basic bar magnet might look something like this, with a north and a south pole. And around it, it will have a magnetic field. And you may have done this with some iron filings at some point in your education, where you showed the magnetic field in this kind of orientation. Now, magnetic fields always go from north to south, so we're going to be drawing some arrows on there showing that it's going from north to south. And you might have shown some iron filings on there to show this pretty picture in the past. But obviously, magnetic fields get a bit more interesting when you start to combine two different magnets and the poles of them. So say I've got a north pole here, and then a south pole here. What we end up having is magnetic field lines come out, as you would imagine. As we showed in the previous video, they come out of the North Pole and go into the South. And you'll notice quite nicely here that these actually line up with each other, and what happens is they join together like such and create an attractive field which pulls these two together because the field lines match up. This is what causes attraction. What causes repulsion is when we have something slightly different. Say, for example, we have a North Pole against another North Pole. And as a result of these two North Poles, we have our magnetic field lines coming out. And you can see that the arrows are pointing in opposite directions now. And as a result of this, what tends to happen is this effect here. These kind of lines bang into each other and they cause this repulsion that stops them from coming together. And it's that interaction of those field lines which causes this repulsion effect in this circumstance. But obviously that's very simple, and we need to look at more complex kind of situations for magnets. So say, for example, we have a wire with a current running through it. Now we're going to say that the current is running into the page, so we represent that with an X, that's into page. And we can also represent a wire with a current coming out of the page, so out of. And there's lots of interesting ways of thinking and remembering this convention. You can imagine it's an arrow going away from you. You see the feathers on the back of an arrow as it goes away from you, and when the arrow comes towards you, you see a point of the arrow coming towards you. So a nice little way of remembering it. So out of the page, into the page. So how do we draw the magnetic field around these wires? Well, quite simply, we use the right-hand rule. Now the right-hand rule utilizes your thumb as the direction of current, that's conventional current from positive to negative, and your fingers show the direction of the magnetic field. So if I put my thumb in this direction now, so my thumb is going into the board, and you'll see that my fingers are curling around in that direction. And so as a result, we can draw a magnetic field with the field in that direction. So guess what for this one? Magnetic field, strength, current coming out of the page. My fingers wrap in that direction. So in this circumstance, the magnetic field travels around in that orientation. And notice how they're just the opposite way rounds of each other. But we can put this to use now in terms of thinking about this in combining magnetic fields around current carrying wires with magnetic fields in for a permanent magnet. So we're going to look at seeing if we can combine these two together. So we have, and you will have in your laboratories, these polarized through the thickness magnets. Now, polarized through thickness magnets just means that you've got a north pole there and the south pole's on the other side, rather than the conventional bar magnet of a north pole and south pole there. So we've got two of these magnets, and as a result of this, we have our magnetic field going across like that. Now, what happens when you introduce a wire with a current in that field? So we're going to introduce a wire with a current. Now, this is going to feel a force because there's a magnetic field around this, and this has got a magnetic field. And as you well know, when you get two magnetic fields interacting, you get either attraction or repulsion. So what kind of attraction or repulsion is this going to feel? Well, we'll need to introduce Fleming's left-hand rule. Fleming's left-hand rule: thumb is the motion or the force that will be felt by this wire in the current carrying wire in the magnetic field. First finger field, that is in the direction of the field, and your second finger sticking out here is the current. So my current is going into the page. I'm going to line up my field finger with the field that's there, and as a result you can see which direction my thumb is pointing. It's pointing directly down. So the force that is felt by this is directly down. But why? Well, this is because this has a magnetic field around it, as we well know from the previous page. And from the right-hand rule, we know that it's going in that direction. And what this causes to this magnetic field, it causes this magnetic field to be disrupted. And what happens is it follows along and gets this distorted shape here. Now, the thing is about magnetic flux lines or field lines is that they have a tendency to shorten and straighten. And it's that tendency that makes them exert a force. Because when this magnetic field gets introduced, it disrupts the field that was there, the green one. And because of that disruption, it causes them to be bent. But because of the tendency for them to shorten and straighten, what happens is they exert a force. And that force is in that direction. So let's have a look at this the opposite way round now. We've got our north pole, we've got our south pole, we've got our magnetic field lines going in the same direction as before, but this time we're going to have a wire with a current going in that direction, so the magnetic field in the opposite direction. So let's draw that one in. Going in this direction. And from Fleming's left-hand rule, let's line it all up. So we've got the field, current coming out of the page, and my thumb represents the motion. So it's going to feel a force in that direction. Why? Well, because we get this same situation of the distortion of these flux lines, which, as a result of this, causes them to want to shorten and straighten, and that exerts a force upwards. So this is two examples of what happens when we have magnetic field lines interacting. And we're going to start introducing and talking about them as flux lines very shortly, especially when we introduce this concept of magnetic flux density and flux linkage in the next couple of videos. But for now, this is basic magnetic fields, and we'll have a look at this in lesson next time.